Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So in this week we have seen the fundamentals of plasmonic resonances, discussed about LSPR and SPP and so on. So I just wanted to record a short video on analytical calculations of optical properties using Mie theory. The reason I want to do this is this: nanophotonics is a frontier area and a lot of things keep changing over time. And it's very useful if the students are able to understand the fundamentals in a very good way. But for that, the learning barrier sometimes is very steep. And in order to address more complicated problems, they have to develop insight, which is only done by working through some relatively simple analytical techniques. Okay? One such technique that I'm very fond of is Mie theory. So it lets you calculate the scattering cross section of a nanoparticle, be it a metal or a dielectric. So in this week I have shown these graphs wherein we are talking about the scattering cross section, and I said, okay, there is an electric dipole and then there's a higher order modes and so on. I even showed you this plots wherein the cross section is given as a function of diameter, and then you have these various field profiles and so on. So these are all calculated using an analytical tool, and it's very useful if you are a researcher working in the area of nanophotonics, a PhD student. It definitely is useful to spend maybe a week in trying to understand some of these things, because it will help you in the longer run. Alright. If you are somebody who is just trying to get a understanding of the subject and at a high level understanding, then I would suggest that you skip this particular video. But if you are somebody working in this research area, then you should try to work it out yourself. So what I'm going to do is I'm going to show you the code, okay, that I have used to calculate. So this is basically a Python notebook, Ipython notebook, which you can use, which you can run using a software known as Anaconda. So using that, I've actually put this on GitHub. So if you go online and look for a repository called as NQP Public. So it's hosted under my name. So search for Naresh Mani. If you search for my name on GitHub, and then you will find a folder which is essentially this. So and if you go in there, you will find the notebooks that are available. So for example, here there's Mie theory notebooks, and in that, let me first look at let's say Mie silver. Okay, so this is the notebook that will load, and essentially I've tried to explain the basic concepts in this. Okay, the theory is involved. So I've taken this from this book, Absorption and Scattering of Light by Small Particles by Craig Bohannon and Donald Huffman. So this is a standard reference book everyone in the world uses. And then there is also some MATLAB implementation available online. So what I've done is I've taken that and then I've tried to write a Python code. So basically this is a summary of it. So essentially when you try to calculate the scattering efficiency, you should go and read this book in the 4th chapter that will have more details. But in essence, you have the various input parameters like the radius of the sphere and then the wavelength at which you want to calculate the cross section. Based on that, and also the refractive index of the medium and so on, right? Medium and the surrounding. If you have those parameters, you will be able to calculate the basic parameters, and then using that and certain functions which are essentially based on, you can calculate these A and B coefficients which are known as the Mie coefficients. Okay, A coefficients represent the electric moments or electric moments, so be it electric dipole, electric quadrupole, octopole and so on, and the B coefficients represent the magnetic dipole, quadrupole, octopole and so on. So there are some expressions which are simple. I mean, these are not very complicated. You can implement them. At first, sight, it might look like these are very, tedious, but yeah, you will be able to implement. If you spend a couple of days on this, you will actually work it out. And so once you have these coefficients, you can easily sum up, the scattering cross section, extinction cross section, and also the absorption. Absorption cross section you will be able to calculate. All right. So the summary of the entire thing is given in this slide. And if you want more details, of course, you have to read the textbook. All right. And yeah, this J, N essentially are the Bessel functions, spherical Bessel functions. And so I have taken, a little bit of, I've provided a brief summary of how to calculate them as well. So Jn and Hn are the spherical Bessel functions, and then you can actually, there are certain things called as recurrence relation. So first you know the first Bessel function of the 0th order, and then you can calculate using that to higher orders and so on. So there is a relation that you can use. So all of this is implemented, just this is the background that, if you are interested, you can just understand that. Alright. And so finally here is the code. So some routine libraries are imported into the Python notebook. And then of course the metal function. In this case I am actually calculating the scattering cross section for a metal. So you see that there's a lambda for various. These are taken from this reference. This is a standard. Johnson and Christie is a standard reference for plasmonics. So you have the various lambda, and then you have the refractive indices and the n and k values essentially. Okay. So based on that you can actually compute. So this is how the real part of refractive index looks like as a function of wavelength. So we expect that this is what we have seen already. So metal. So above a certain frequency, which is a plasma frequency, it is metallic, so it's negative, and up at about 800 nanometers, it's roughly 30 plus minus 30 or minus 32 or so. So negative real part. Imaginary part I have not shown you, but you can actually compute. I mean, already done this here, so you can actually plot it and then calculate and then check it out yourself. So once we have the basic properties and the wavelengths and so on, you will be able to just interpolate the various lambdas and then calculate. So this is where the Mie coefficient, this particular function, there is some annotation, you can look at it to understand what it is. So the Mie coefficient is calculated here. Various Bessel functions are first calculated, and then the relationships are applied, and then finally you get the coefficients. So A and B coefficients are returned by this function. So once you know that, you can easily compute the scattering cross sections. Alright. So the size parameters and all that is explained already what it is. So once you have this, you plot the data. It's basically a lot of text essentially to try to make it look nice, and this is what you finally end up with. So if you look at the cross section, scattering cross section, you see that this is actually normalized to the geometric cross section. So that's why the number is up to 10 or so, and then you have extinction, which is basically a sum of absorption and the scattering cross section. So this is what it is, and you can easily change the diameter. For example, here let me say I want to now calculate it for a diameter of 100. This is a local one. So I have opened this notebook, and for example, now let me go and compute for diameter of 100 nanometers. So my refractive index, this is the radius of the particle. So radius I'll make it 50. So once I do that, then I can just if I shift enter, it will run. So I mean, some of these things you might have to know. So it might take a little bit of time to familiarize with Python, but it's a pretty nice tool. So then these things are calculated. Now we can plot it. So this was for 50 nanometers. Now you see 100 nanometers. You see the red shift in the resonance. Similarly, if I go back and change it to 125 nanometers or something, it'll 75 nanometers. If I make it, it'll even more red shift. So in this just one single file, everything is present. So it will help you learn. Okay. You see that, you see whatever we showed in the slides, this is what you have. We cleaned up a little bit and put it on the slides. So you see that the absorption is not that significant. Most of the loss is coming from the scattering. Alright. So this is what it is. So I've hosted this. So please go to GitHub, search for NQP, Naresh Himani, NQP public. This is a repository where I'll try to add as much as I can. In the next week, we are going to talk about transform matrices. So T matrix code, that also I will try to put into this. So hope you can use some of these things to learn by yourself. So this is not something that is going to be, the details cannot be taught in a course. It has something that you have to do it by yourself. But I have given you a working code. So with that, I think you will be able to figure out. All right. So that's it. I just in the next I have also added one more notebook for dielectric nanoparticles. I didn't talk about dielectric nanoparticles this week, so maybe in the next week I'll take a 5-10 minutes and then I'll talk about the dielectric nanoparticle as well. But even further, the code is given. So in this case, this is for silicon, and the data is taken from PALIC. So I just put the data here, and then you see the same code essentially. It's just that the refractive index changes here. N sphere will be different. In previous case, N sphere was we essentially took the data and then created a function, interpolation function here, and then used that to generate the refractive indices. So you have this, and then that's it. You calculate the same data essentially, same code will calculate. In this case, you will see a little bit more interesting features in the scattering and extinction coefficients, cross sections. So we'll talk a little bit briefly in the next week in the first part. 5-10 minutes I'll spend on this, and then I'll talk about electromagnetic wave propagation in the periodic structures. All right. So thank you so much. We'll see you next week.